Consider the following languages over the alphabet. Sigma equal to A, B, C. Let L1 equal to A raised to n, B raised to n, C raised to m such that mn greater than or equal to 0, and L2 equal to A power m, B power n, C power n such that mn greater than or equal to 0. Which of the following are context-free languages? We have two options, L1 union L2 and L1 intersection L2. So they have given us two context-free languages here, L1 and L2, and they are asking which of these are context-free. If we take union or intersection of these, which of these are also context-free languages? So let's go to statement 1, L1 union L2. Now two context-free languages are always closed under union. So the reason for that is, I'll show you the proof for that. Let us say for each language L1 and L2 we can write the corresponding grammar for it. Suppose S1 is the starting symbol for the first grammar and S2 is the starting symbol for the second grammar, let us suppose. Meaning the first grammar will look something like S1 gives something, etc., and the number of productions here. Similarly S2 will also look like S2 gives something and some productions here. This is the grammars for the language L1 and L2. Now if I try to create a new grammar S such that S gives S1 or S2, S1 gives whatever were here, S2 gives whatever were here, and all the productions here. If you take a look at this, this is also a context-free grammar. It satisfies all the rules for a context-free grammar, as well as this generates a union of S1 and S2. S initially gives either S1 or S2, and S1 will give all the strings in S1, S2 will give all the strings in S2. So this is showing that union of two context-free grammars are also context-free. So this part 1 is true. Context-free languages are closed under union. Now second is intersection. Context-free languages are not closed under intersection. If we take the intersection of two context-free languages, the resulting one may or may not be context-free. It is not guaranteed that the intersection is context-free. So we'll take this example and take the intersection and see if it is actually context-free or not. So L1 is A power n, B power n, C power n, meaning the number of A's and B's should be equal, and then there will be a number of C's after that. So L1 is a set of all strings of A's, B's, C's such that number of A's equal to number of B's. L2 is a set of all strings A's, B's, C's such that number of B's equal to number of C's. Now intersection of these two will be the set of strings that belong to L1 and L2 both. Meaning that for any string belonging to L1 intersection L2, the number of A's should be equal to the number of B's to satisfy L1. Also the number of B's should be equal to the number of C's in order to satisfy L2's condition. That's what I have written here. So what it implies is that the number of A's should be equal to the number of B's and number of B's should be equal to the number of C's, meaning number of A's, B's and C's all should be equal to each other. Meaning L1 intersection L2 is nothing but A power n, B power n, C power n such that n is greater than or equal to 0. All should be equal to each other. Now this is not a context-free language. This is a context-sensitive language. The proof of that you can look in the video lectures and see that even if I keep on pushing A's, then for when I see B's, for the push down automata for this language I can keep on pushing A's, and when I see I can either pop A's or push B's. But then again for C also I have to equate it to A and B. So this I can't do it via a push down automata using a single stack. You can see the proof if you refer to the video lectures for context sensitive languages section. So this is a context sensitive language, it's not context free. So L1 intersection L2 is not a context free language, meaning the right answer is option A, statement 1 only.